Alright guys, today we're talking about section 2.3. This is about evaluating limits analytically. In previous discussions we've talked about evaluating limits via a graph, evaluating limits via a table of values, and then we talked about using the formal definition of the limit to prove a limit exists, that is using the epsilon delta definition. Now, today we're going to look at evaluating limits analytically, and by that I mean using algebra, factoring, multiplying by conjugates, maybe doing some trig and stuff like that. Okay, now a major theme of the last class or so has been to evaluate a limit, use direct substitution if possible. Now, what do we mean by direct substitution? We mean this, okay? The limit, we can say if f of c is defined, then the limit as x approaches c of f of x is equal to what? It's just equal to f of c. That is, if you can just plug in c into your function, then do it. Now the problem is that usually the reason we're looking at a limit to start with is because f is not defined at c. But you will be thrown a softball every once in a while, and make sure that you can solve it. Okay? That is, if you can use direct substitution, go ahead and use it. Okay? That's what you want to do. Now, here are a bunch of limits. I put them here just because we need to be able to use these fluently. Okay? That is, if we can factor out a constant called a scalar multiple, factor it out, then find the limit. If you can break a sum or a difference apart and it makes things easier, do it. If you can find the limit of two, if you have the product of two functions and you can more easily find the limit of those two factors individually, do that, then multiply the two solutions. Okay? These we need to know these backwards and forward. Okay? I'll give a quick example illustrating a couple of these. Let's say we have the limit as x approaches 2 of, let's say 2x squared plus 4x. Okay? Just a polynomial. Now, clearly, this polynomial is defined at x equal 2. C is 2, and we can simply evaluate f of c. Now, but what's going on behind the scenes? Behind the scenes, we could say this is equal to, using part 2 of our theorem 2.2, we could say this is equal to the limit as x approaches 2 of 2x squared plus the limit as x approaches 2 of 4x. So we took the sum and broke it apart. You'll often hear me say that the limit of a sum is the sum of the limits. Okay? But now we can use rule number 1, property number 1 over here, because we can factor out a 2 and factor out a 4. We could say this is 2 times the limit as x approaches 2 of x squared plus 4 times the limit as x approaches 2 of x. And then finally we can say, okay, x squared is defined at 2, x is defined at 2. Let's use direct substitution and say 2 times 2 squared plus 4 times 2. And what we have here, we have 2 times 4, so that's 8 plus 8 equals 16. Okay? And that's kind of what's going on behind the scenes. Now, I don't necessarily expect you to show me every step here, because we know that you can simply use direct substitution. However, there will be situations where you need to use these properties and limits, and you won't be able to simply just use direct substitution. That's why you need to be very fluent in all of these properties here. Okay. Another special case I want to look at real fast is the special case of a constant function. Let's look at the limit as x approaches, let's say 6 of 4. Okay. This is the constant function of 4. Okay. Now, when we say to use direct substitution if possible, here's something that trips lots and lots and lots of people up. Lots of people just want to say, answer 6. Hey, I substituted. But that's not the answer, and I hope you can see why. This is a constant function of f of x equals 4. What does a constant function look like? A constant function is a horizontal line with a y-intercept, in this case of 4. So let's say 4 is right there, or excuse me, not 4, but 0, 4. Okay, and then there is the horizontal line that passes through 0. Oh, that's not very horizontal, but there we go. Okay, now what is every y value there? By definition, every y value is 4. So if we in particular look at x equals 6, what are the y values? Let's say x is 6.1, or let's say x is 5.99. What do those y values look like? Those y values look like 4, because every y value is 4. So be careful in that situation. Okay, don't be just not thinking about this, thinking it's a super easy directly substitute. I mean, we are using direct substitution here, but it's kind of funny because no matter what we directly substitute, f of that value is 4. I mean, if I said, what's the limit as x approaches e of 3? Actually, let's make it look even weirder. Pi. Okay? That looks crazy. But this is a horizontal line with a y-intercept of pi. So every y value is equal to pi. In particular, the x value, the c value e, which is the base of the natural log, so about 2.7 and change, around that x value, what do the y values look like? Still pi. Okay? That's how constant functions work. So don't let, probably the easiest problem you'll have all semester, don't get tripped up on it. Okay? Now, this is direct substitution. What about when direct substitution fails? Okay? Let's get ourselves a little room here, because this is where things get interesting. Let's see here. Let's go a little more. What if direct substitution fails? Okay, that is f of x is not defined at x equals c. Okay? Well, that's when you have to get a little creative. Now, there's going to be a few different techniques here. Technique 1, divide. Oh, actually, I'll be a little more specific. Factor and divide. Okay? This is probably going to be the most common. That is, we're going to try to rewrite, in all of these, we're going to try to, or in the first two rather, we're going to try to rewrite the function so that we get a new function that agrees with the old function everywhere except at x equals c. That new function will then be defined at x equals c, then we can use direct substitution. Okay. Second technique is going to be, let's see, use conjugate of numerator. Actually, that's fine. Use conjugate of numerator to rationalize numerator. I simply should have said rationalize numerator, but I guess maybe I was being a little more specific here. That's fine. Okay. Third, and then this won't be as common, but we will use this. We have something called the Squeeze Theorem. So we'll tackle these in this order. Factor and divide, that's going to be the most common. Conjugates, rationalizing, we're going to, clearly you use that when you have radicals involved. So there's your hint there. If you have a limit that you can't use direct substitution and it has radicals, good chance you're going to need to rationalize the numerator. Okay? Let's look at a quick example. We actually looked at this the first day of class, or actually maybe the second day of class. We looked at the following limits. We looked at the limit as x approaches 1 of the rational function x cubed minus 1 over x minus 1. Now, when we looked at this the first or second day of class or so, we looked at this graphically. Okay? But clearly, we can't use direct substitution. We want to analyze this not graphically, not numerically. We want to analyze this what's called analytically. So we want to use some algebra. Now, here's what we need to do. Since this function f is not defined at x equal 1, we want to rewrite this function into a new function g such that f and g are identical except at the point 1, except at c. Now, how do you do that? Well, it's easy. Factor and divide. Okay, we could say this is equal to the limit as x approaches 1. Now, that's the difference of two cubes, correct? Difference of two cubes is going to factor like x minus 1 times what? Well, if you remember, the pattern here is going to pan out to be x squared plus x plus 1. Okay? And then, of course, we still have the factor on the bottom of x minus 1. But what's the beauty of this? The beauty of this is those two factors cancel out, they divide out, leaving us with the limit as x approaches 1 of x squared plus x plus 1. Okay? Now, just to be clear, this is f of x. This is g of x. F of x and g of x except at x equal 1. And that's what we want. We want a new function g that agrees everywhere with f except at that particular value of c. But now the beauty is that we can now directly substitute because this function is defined at c. So by direct substitution, we have 1 squared plus 1 plus 1 equals 3. And that is what I mean by using the factor and divide method to analyze a limit analytically. Okay, this is probably going to be the most common way to evaluate limits when direct substitution fails. Let's look at another one real fast. Let's see here. Let's look at the limit as x approaches -3. X approaches -3. This isn't going to be too hard. It's x squared plus x minus 6 over x plus 3. Okay, clearly f of x is not defined at x equal -3. If you try to plug in x equal -3, clearly you get a 0 on the denominator. That's a bad deal. Okay, so what you want to do is try to factor and divide. So let's find a new function g that agrees with f everywhere except x equal 3. So let's see here. How can we factor the top? Well, just remember your algebra class rules. I think we can factor this as x plus 3, x minus 2 over x plus 3. Cancel out, and we're left with the limit as x approaches negative 3 of x minus 2. This is just a linear function. Now, again, this linear function g of x agrees with this function f of x everywhere except in this case at x equals, let's see, at x equals negative 3. They agree everywhere else except at x equals negative 3. Okay. So let's see here. In fact, this right here, that is a linear. The graph is a line with a hole in it. Here, the graph is a line that looks exactly the same, except there's no hole here. Okay, but the limit's going to be the same. And by direct substitution, I should have had equal signs here. And we can say by direct substitution, negative 3 minus 2, which equals negative 5. Okay? That is the dividing out technique. Okay? What about a hard one? Here's a tougher one. Limit as x approaches 0 of 1 minus e to the negative x divided by e to the x minus 1. Okay? Let's see here. Yeah, we have e to the x's. This one looks kind of tough. Let's see how it plays out. If we try to use direct substitution, let's see. The denominator specifically here, e to the 0, that's e to the 0 is 1. 1 minus 1 is 0. But it turns out the numerator is 0 too. So we have a problem here. We have 0 over 0. It's something called indeterminate form. We'll be talking about that a lot here in the future. But all you really need to worry about now is that there's a 0 on the denominator. So we can't use direct substitution. But let's see about rewriting this such that we can. Now, let me think about this. What I want to do is rewrite this somehow that when I directly substitute for 0, I don't get a 0 on the denominator. Oh, here's an idea. What does this actually look like? That actually looks like 1 minus 1 over e to the x. E to the x minus 1. Okay. What if I multiplied on the top and the bottom by e to the x? Let's see if that works. I have a hunch that it might work. So I multiply on the top by e to the x and on the bottom by e to the x. Okay, so I'm just multiplying by a fancy version of 1 there. E to the x over the x, that's multiplied by 1. Okay, so I multiply every term on the top, and I don't think I'm going to need to multiply. Well, I'm going to multiply by every term on the bottom. I'm not going to distribute though. Okay, so on the bottom I'm going to leave it like so. E to the x times e to the x minus 1. I might have to distribute that. I don't think so, looking ahead here. On the top though, if I distribute that e to the x, I'll have e to the x minus e to the x over e to the x. Okay, which equals the limit as x approaches 0 of e to the x minus 1. Oh, there we go. I was right. I love it when my hunch is right. Look at this. Factor, factor. Exact same thing. So limit as x approaches 0 of 1 over e to the x. Now, let's bring back our purple highlighter. Here is f. here is G. F and G, they agree everywhere except, in this case, x equals 0. But the beauty is that this F is not defined at x equals 0, whereas this one down here, G, is. This equals, by direct substitution, 1 over e to the 0 equals 1 over 1 equals 1. Perfect. Okay? Now that one I thought was going to be a lot harder than it was. Now it would have been harder if you just didn't I've been doing calculus for a long time here, and so I kind of have a way of looking at these and kind of figure out here's a direction we need to go. If you didn't have that hunch of a direction to go, that would have been really tough. Okay, so there again, the reason I saw that was that I looked at this term right here and thought to myself, hey, I should rewrite that and see if anything pops out at me. Okay. Again, you're just trying to change forms here to get to a form that's good. Now, in fact, I didn't realize when I picked this problem, we didn't really, did we factor and divide out? We didn't factor, but we divided out, I guess. Okay, so I guess that fits the bill for that first technique, even though we didn't factor, but we divided out. Okay, let's pick one where we do have to factor out. Maybe let me pick one a little better this time. Let's see here. Limit this, because I like this one. This one looks really weird. As x approaches the natural log of 2. That looks weird. But again, that's just a number. Okay. Now, of what function? Now we have a rational function. It is e, we have a real nasty rational function, e to the 3x minus 8 over e to the 2x minus 4. Alright, that looks bad. Okay, especially that c value, natural log of 2. But here, I hope you can realize this looks like we can factor, this looks like we can factor. Okay, now, again, you have to go back to those solid algebra skills that you need to have. Let's look here. Limit, let's put an equal sign there. Correct notation here, as x approaches natural log of 2. Oh, I guess I should say, why can we not use direct substitution? Look at the denominator. If we look at, okay, I'm going to do this off to the side. Maybe I'll erase. Or actually, I'll just do it here in pink, so it'll be off to the side. E to 2 times x, but natural log of 2 minus 4. Okay, that can be rewritten, okay, as, let's see, we could rewrite that as e to the natural log, of 2 squared. Again, remember the rules of logarithms. You can take that 2 and put it as an exponent of your argument. But what if you have this situation, minus 4, if you have this situation, e to the natural log, those are inverse functions, so you get 2 squared minus 4, 0 on the denominator. So that's why we can't use direct substitution, because direct substitution yields a 0 on the denominator. Okay? And in fact, let's see, if you did the exact same thing, you would get a 0 on the numerator, except you would have a 3 there instead, and minus 8. But 2 to the cube minus 8 is 0. So you get 0, 0. Okay? Now, let's try to factor this. Let's start at the bottom. Bottom is easier to factor. Okay? In fact, let me rewrite it first, then we'll factor. Actually, I'll rewrite the top and the bottom. E to the x cubed minus 2 cubed. E to the x squared minus 2 squared. Now, if you didn't recognize that, this would be impossible to do. That's rules of exponents. Remember, if you have an exponential expression raised to another power, you can multiply the exponents. Well, I did the reverse of that. So I just rewrote it. Okay, we can say this is equal to the limit as x approaches the natural log of 2. Now let's factor. Let's start with the bottom. The bottom is easier. That's the difference of two squares. E to the x minus 2, e to the x plus 2. Okay. Now, that's a difference of two cubes. How does the difference of two cubes factor? Okay, let's say that's a and that's a b. So the difference of two cubes factors is a minus b, e to the x minus 1. Oh, undo. E to the x minus 2. Okay, and then what's left over when you have the difference of two cubes? It's e to the x squared, it's a squared, plus a times b. Okay, a times b here, so we have, e to the x, so 2e to the x, 2e to the x, and then plus b squared, so plus 2 squared. Okay, now, why is that really nice? That is really nice because that and that. So what's left over here? Let me erase real fast. Gives ourselves a little more room. What's left over equals the limit as x approaches the natural log of 2 of, let's see, e to, we can just say 2x now. E to 2x plus 2e to the x plus 4 over e to the x plus 2. Now we can use direct substitution because this denominator is not going to be 0 because it's e raised to a positive power plus 2. So there's no worry here about getting a 0 on the denominator, and we can say via direct substitution that this is, let's see, e to the 2 times the natural log of 2 plus 2e to the natural log of 2 plus 4 over e to the natural log of 2 plus 2. Okay, now what did I say this was earlier? Okay, remember you can take the 2 to the power of your argument of the natural log function. So it's going to be the natural log of 2 squared. But e to the natural log is just going to result in 2 squared, okay, plus 2 times this. Those are inverse functions, so just 2 is left over with a coefficient of 2, plus 4 all over e to the natural log of 2, 2 plus 2, let's see here, a bunch of 2's, 4 plus 4 plus 4, so that's 12 over 4 equals 3. Now, hopefully I didn't make an arithmetic error anywhere, but that's an interesting example. I like that one, okay? Again, you have to make sure that you know how to do the difference of two cubes. Now I have my fingers crossed. Hopefully I remember the difference of two cubes correctly. I always get, I'm going to be honest with you, I frequently get like the negative signs mixed up here, but I think I did that right. Okay, so just to recap here, direct substitution failed. There's f of x. Here is g of x. F of x and g of x are exactly the same, except at x equal natural log of 2. Everywhere else, if you graph those two functions, they would look exactly the same, except there's a hole here above the x value natural log of 2, and there's not here. But they will have the exact same limit. Okay? That is the dividing out technique. Again, pretty easy, like right here, easy. Factor, divide out. Here, not so bad. As long as you have a difference in two cubes, not so bad. Here, took a little more work. Yellow down here, took a lot more work. Okay, but that's the factoring and or dividing out technique to find limits analytically. Again, this is when direct substitution fails. That's technique 1. Now, what about technique 2? Technique 2 is to use the conjugate of the numerator to rationalize the numerator. So let's look at an example. Let's look at the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Now, we want to use direct substitution. Clearly, direct substitution fails. If you look at f of 0, well, 0 occurs on the bottom immediately. But then if you look at the numerator, a 0 will occur on the numerator as well. But again, this is called indeterminate form. We'll learn much more about this in the coming days. So all we're concerned with right now is that direct substitution fails. So how do we fix this? Now, factoring this immediately, there's no way to factor it that I know of just immediately. I mean, you have an x on the bottom and you have the numerator or so, but here's the key. Let's rationalize the numerator. Now remember, what's rationalize the numerator? That means you multiply by the conjugate of the numerator. So we can say this is equal to the limit as x approaches 0 of the square root of x plus 1 minus 1 times its conjugate. The square root of x plus 1 plus 1. We had an x on the bottom, but remember, if you do it to the top, you have to do it to the bottom. Square root of x plus 1 plus 1. So I'm multiplying on the top and the bottom by the conjugate of the numerator. Now what happens here? Now what's the whole point, or what's the convenient thing about conjugates? Okay, remember, if we FOIL this numerator, the two middle terms are going to add to 0. So what we're left with, and once you do the algebra, is x plus 1 squared minus 1 squared over the square root, or excuse me, x times the square root of x plus 1. Let's do a little erasing here. Okay. Plus 1, like that. Let's see here. Equals the limit as x approaches 0. Now what does that equal? That is x plus 1, the square root of that squared, so just left over the x plus 1. X plus 1 minus 1, you just left the x, times x plus 1 plus 1. But notice there, that can cancel out with that. So we're left with the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now is that defined at x equals 0? It is indeed. Equals 1 over 1 plus 1 plus 1. Okay? Oh, not 1 plus 1. I was about to say, that's not going to be a pretty answer. The square root. I'm trying to write too small. The square root of 0 plus 1 plus 1. Which equals what? Well, that's the square root of 1 plus 1. 1 divided by that, 1/2. Just to recap, f of x is not defined at c, but g of x is defined at c. F of x and g of x are the exact same function graphically, except above that one x value, x equals 0. The limits will be the same. That's the rationalizing technique I'm referring to. Let's do one more while we're at it. Let's see here. Okay, let's look at the limit. As x approaches 0, oh, let's change it up a little bit. The limit as x approaches 16 of (4) minus the square root of x over x minus 16. Okay? What happens if we try to use direct substitution? Well, on the bottom, a 0 is very clear occurs. On the top, also a 0 occurs. So we cannot evaluate this limit using direct substitution. If you have radicals, a good idea is to use the conjugate technique. So let's multiply the top and the bottom by the conjugate of the numerator. So we're going to rationalize the numerator. So 4 minus the square root of x times 4 plus the square root of x, x minus 16, 4 plus the square root of x equals the limit as x approaches 16. Now, we know for sure that the two, but since we're multiplying by the conjugate of the numerator, we're going to be left with 4 times 4, so 16, minus the square root of x squared, so minus x, okay, over x minus 16 times 4 plus the square root of x. Now look what happened here. We have a 16 minus x and an x minus 16. Those are super close together, super similar, but they're not the same thing. So we can't just say, oh, same factor, and move on. What we have to do is do one more step of factoring. Now you can do this either on the top or the bottom. I'll do it on the top. Let's factor a negative 1 out of the top. I know it looks funny to do so, but this is a technique you need to get accustomed to. Factor a 1 out, or excuse me, a negative 1, we'll be left with negative 16 plus x. Now why is that true? Because if I distribute back, it would be negative 1 times negative 16, positive 16, negative 1 times positive x, negative x. Now, since we all agree that that's true, let's just go ahead and rewrite it. X minus 16. Then we have x minus 16 over 4, like so. Now we can say similar factors. That leaves us, let's see here, with a negative 1 on the top and a 4 plus the square root of x on the bottom. Now, can we directly substitute? I think the answer is yes. This function is defined at the c equals 16. So we can say equals negative 1 over 4 plus the square root of 16 equals what? Negative 1 over 4 plus 4, negative 1/8. Done. Okay? So there was that new little curveball thrown in there about factoring in a negative 1. That happens a lot of times though. So if you ever have two factors on the top, one on the top and on the bottom where they're almost the same except the reverse sign's reversed, factor out a negative 1. Just to recap, f is not defined at c. We converted via some algebra to a g of x that is defined at c. And that is our second technique. It's called rationalizing the numerator. This is typically what you're going to use when you cannot use direct substitution to evaluate a limit and f of x has radicals in it. So it has roots in it. Square roots is typically what's going to happen. Okay? That is our second kind of tool in the toolbox for analytic limits. Now, let's look at the third tool in the toolbox, and that's something called the Squeeze Theorem. And actually, this is going to introduce us to some trig limits. Now, trig is what a lot of people struggle with, okay, but we really have to concentrate and do well on trig It's really important. There's a lot of trig in this class, okay? So let's take a look. Now, the squeeze theorem essentially says that, you know, you can't use maybe you have a situation where you can't use the dividing out technique. You can't factor. Maybe you're dealing with a trig limit that's can't be factored. Let's say that you can't really rationalize either. Okay, so what I'm going to do here is I'm going to motivate by example, and I'll show you what I mean here. If I want to look at the limit as x approaches 0 of sine x over x, okay, with just the two previous techniques, that is rationalizing the numerator and factoring and dividing, they wouldn't help us here. Sine x over x, the top's factor, there's nothing to factor. The bottom's nothing to factor. You can't really rationalize either. You know, you can play around with trig identities, and you're still just going to get problems when you try to directly substitute a 0 in for x. Okay, so here's what the squeeze theorem says. The squeeze theorem says that if you can find two functions, so this is, let's say that's f. If you can find another function, let's say g, such that g of x is less than or equal to f of x, and another function, let's call it h of x, if you can find two functions, one above f and one below f, and then you can take the limit as x approaches c of g of x, and it equals, let's just say, some number a. And you can take the limit as x approaches c of h of x, and it also equals a as x approaches c. Then guess what? This implies that the limit as x approaches c of f of x has to also equal a. So you squeeze f of x between h and g, and that's how you can get a limit. Now, how might we go about doing this? I think this is one of those just really important proofs that you're going to see in every calculus book when we talk about explaining this limit here. Okay, if you want to know why it works. So let's look at why it works. It's kind of cool how it works. So let's see here. I'm going to try to draw a picture here. Let's see how it works out. So I'm going to draw. Oh, that's not what I meant to do. Sorry, I hit the wrong button. Let's draw the first quadrant of a unit circle. It's not perfect, but it'll get the job done, I think. Okay, now this is a unit circle, so this point right here is 1, 0, and that point right there is 0, 1. Okay, that's important. Let's look at a triangle. Okay, let's look at a triangle drawn straight up and like this. Oh, that's bad. That's bad too. There we go. Now, let's look here. And then let's also look, so we have a couple different triangles here. Oh, that's not a very good line. That's not either. Let me concentrate here. There we go. That'll get the job done. Now, let's look at a few things here. So we have, and I'll maybe do different colors here. So we have this big triangle right here. Okay. We also have this small triangle. And we also have this sector of a circle. So let's see, I'll do that in purple. Now remember what the sector is? The sector is like a slice of the pie. So it's like a slice of pizza. So it's like a triangle there, but it has that curved edge. Okay? Now let's see, I want to put a little bit of green back in there. So I have the small triangle, that's the green triangle. Okay? I have the big triangle, that's the pink triangle. And then I have the purple, sector of a circle. Now, let's refresh our memory on trig. And let's think about those two objects. Which one's the smallest? The area of it. Well, the area of the green triangle here is the smallest. Okay, I know it's kind of have a lot of overlap here, but the green triangle is the smallest. Now, how would we find the area of that green triangle? Now, that green triangle has a height like this. It's called the altitude of the triangle. Now, what's the base of the triangle? Now, we drew this on a unit circle, so the base of that triangle is 1. Okay, so let's say the area of green triangle, oh, that's a bad triangle, equals, okay, it's 1 times the height of the triangle over 2. Now, what's the height of the triangle? Now, let's think about this. If this is theta right here, or let's type in theta. Theta is that angle right there. Okay? If we look at, let's think about our trig functions, sine, cosine, tangent of theta. This is a unit circle, so what is this length right here? That's a diameter of the circle, so that has a length of 1. Okay? So think about this. Sine of theta is opposite over hypotenuse. Opposite is that exact altitude I'm looking for. So I can say the height of that triangle is sine theta. So the area of the green triangle is simply sine theta over 2. Okay? Now, remember, we were looking at 3 shapes here. We were looking at the green triangle, the purple sector, and then the pink triangle. Well, the purple sector is kind of the thing in the middle. It has the middle area. The green triangle has the smallest area. The purple sector has the area that's somewhere in between of the green and the pink triangles. Now, how do you find the area of a sector? It's really easy if you remember it. The area of a sector is r squared theta over 2. Now, what's r squared here? That's the radius. Well, the radius is 1. So r squared theta over 2, that's easy. That's 1 squared theta over 2, or theta over 2. Okay? Then let's look at the area of the big triangle. Area of the pink, which is the big one, triangle. Okay? We know that the base here is, since the base is on this unit circle, it goes here, the base is 1. So base times height over 2. Now the question is, base times height, what's the height of this triangle? What's this height right here? Okay, let's think about this in terms of theta. Theta, we could say, let's see, we use sine. Cosine might not do us any good, but what about tangent? Okay, tangent is opposite over adjacent, which is nice because this adjacent side has a length of 1. So tangent of theta is the height of that pink triangle, because opposite over adjacent, adjacent's equal to 1. So this is equal to tan, hope I should be a little more neat there, theta over 2. Now, why did I do all of this? I hope you'll like this. I hope you'll be just as impressed as I was the first time. Okay? So this is the smallest figure on that graph. This is the middle-sized figure on the graph, and here's the largest figure on the graph. Okay? So we can say that the area of let's stick with the colors here to color code it. Area green triangle is less than equal to area purple sector less than area of pink triangle. Oh, I should say area pink triangle. Okay? In other words, we can say that what? Sine theta over 2 less than equal theta over 2 less than equal tan theta over 2. Okay? Now, where does this take us? Here's kind of the cool, you gotta remember your trig stuff here, but let's see here. What I want to do is bound this function. Now, I'm using thetas instead of x's, so just imagine I have x's. There's nothing special about the variable x versus theta. So I have thetas down here, but don't worry about that. I want to get this function in the middle. Now, how do I do that? First of all, let's get rid of those 2's. I don't want those 2's there. Okay? So I'm going to multiply everything through by 2. So let's say sine theta less than equal to theta less than equal to tan theta. Okay? Let's get a little more room. All right. Now let's just remind ourselves, I want to eventually get sine theta over theta in the middle. Okay? But I have a theta on the numerator right now, so let's actually get theta over sine theta, then flip the whole thing. We'll have to reverse our signs. That's no big deal. So let's see here. Let's divide everything by sine theta. Okay, so I'll have sine theta over sine theta less than equal to theta over sine theta less than equal to tan theta over sine theta. Okay? Now why is that nice? Sine theta over sine theta, otherwise known as 1, less than equal to, let's see here, that's just theta over sine theta still, less than equal to, okay, off to the side real fast, tangent sine over cosine, right? Sine theta over cosine theta, all over sine theta. Okay? So we have a compound fraction here. We have this fraction divided by sine theta. So this equals sine theta over sine theta cosine theta. There. So this equals 1 over cosine, not x theta. Now this is almost what I want. Look at here. I have theta over sine theta. I want sine theta over theta. So if I just invert the entire thing, that is, invert 1 is just 1, invert the middle term, sine theta over theta, invert the right-hand term, that's just cosine theta. Now if I do that, I have to reverse my signs. Almost there, guys, I promise. Now I have sine theta bounded between two functions, between the constant function 1 and cosine theta. Now let's look at the limit of each of those. Look at the limit as x approaches theta, no, not theta, 0 of 1. What does that equal? Oh, let's do this off to the side. Limit as x approaches 0 of 1. That's the constant function 1. What's its limit as x approaches anything? It's 1. What about the limit as x approaches 0 cosine? Oh, let's say, actually I used x there, so cosine x. What's that limit? Well, cosine is defined for all real numbers, so just directly substitute. What's cosine of 0? Cosine of 0, actually let's go this way. Cosine of 0 equals 1. So look what I've done. I can look at the limit as x or theta approaches 0 of all of these. The left hand and the right hand limit both equal 1. That means by the squeeze theorem, the middle one has to also equal 1. So I can take the limit of this term equals 1. Limit as x approaches 0 of this term equals 1. That forces, by the squeeze theorem, the limit as x approaches 0 has to equal 1 as well, because these two are squeezing that limit must be equal to 1. Thus, this equals 1. Now, that took a whole lot of work. Okay? Guess what? At this point, memorize this. Memorize it. Okay? I proved it for you there. You can look at it online. You can relook at it here. You can look at it in your book. Now we're going to assume that's true. This fact right here is going to pop up in other trig limits. Okay? So don't forget that. There's a few other special limits. Let's look at another trig limit that you should memorize. Now I'll prove why it's true, but you need to memorize it. Okay? Here's again another very, very important trig limit for you to memorize. Okay? Limit as x approaches 0, 1 minus cosine x over x. Okay? If we try to substitute, numerator, cosine 0 is 1. 1 minus 1, you get a 0 on the top. That's not a huge issue. The issue is that you get a 0 on the bottom as well. Again, that's called indeterminate form. Now, how do we solve this? Squeeze theorem doesn't help us here. I mean, it might in some regard, but what we can do here is use one of those previous techniques. We can actually use the rationalizing the numerator technique here to solve this. But we're going to need that previous theorem that previous limit I just proved about sine x over x. Okay? So let's see here. Let's try to rationalize the numerator. So we're going to multiply by 1 plus cosine x over 1 plus cosine x. Let's see what happens here. Limit as x approaches 0. Now, let's see. Let's skip a step here. We know that the two middle terms are going to cancel out, leaving us with 1 minus cosine squared x. Now remember, what cosine, this notation right here means is it's 1 minus cosine x times cosine x. You know, the trig, when you raise trig to powers, it looks kind of funny, but just remember that. On the bottom, we have x times 1 plus cosine x. I'm not going to distribute that. I don't think I need to here. I think it'll actually mess things up. Okay? But let's look at this. Limit as x approaches 0. What do we know the numerator equals? Think back to trig class. Does 1 minus cosine x ring a bell? What about this? Nope. Sine squared x plus cosine squared x equals what? 1. If we rearrange that, 1 minus cosine squared x equals sine squared x. So that's why you really need to have those trig identities memorized. So we can replace the numerator with sine squared x. Then we have x times 1 plus cosine x. Okay? Now, what you need to be in the habit of is recognizing when you might see the pattern where there's a factor of sine x over x. Okay? In fact, let me be more specific with the numerator. Okay, it's sine squared. Let me actually write those two factors out. We can say that's sine x times sine x. But what do you see here? You see sine x over x. And didn't we have a theorem that says if you have a product of two functions that you can take the limit of those two factors individually? Thus we can say equals the limit as x approaches 0 of that highlighted portion, sine x over x, times the limit of everything else. X approaches 0, sine x over 1 plus, sine x over 1 plus cosine x. Now what did I tell you about this? We have proved it. We know what it equals. It equals 1. What does this equal? Well, I don't know, but I think we can use direct substitution now. Because what's sine of 0? Sine of 0 is 0. What's cosine of 0? Cosine of 0 is 1. Okay? So this limit we can evaluate by direct substitution, and that limit is 0 over 1 plus 1 is 0 over 2, otherwise known as 0. So 1 times 0 over 2 equals 0. Okay, guys? So we have now proved this. Now it's time to memorize it. Because just like this right here popped up in this problem, well, guess what? This right here might pop up in other limits. So you might have this occur inside another limit. Now, if you haven't memorized what this limit equals, you'll have to either reinvent the wheel or you'll just be stuck. So memorize this as well as memorize this limit right here. Those are two limits you want to have memorized. Otherwise, you'll have to reinvent the wheel or just miss that problem when you see it on a homework problem or on a test. Okay? Again, I said it a couple times now, memorize those. Now, I'll show you why it's important. I'll show you another example. Let's see here. Let's look at the limit. Maybe I'll do one, maybe two more examples. I know this has been long here, but you know, there's a different situation for every problem you're looking at. I can't tell you, you know, here's the way it's going to work every time. But I can tell you the things to look for, things like this. Now here's another common limit. Let's look at the limit as x approaches 0 of tan x over x. Okay? Well, clearly direct substitution fails, so we can't use direct substitution. We need to rewrite this. Okay? And again, I should say, stress here, here's f of x. We rewrote into a g of x that we could then take the limit of quite nicely. Okay, we need to do the same thing here. F of x cannot be evaluated with direct substitution, so we need to rewrite it. Now, whenever you see a tan x, you should probably be thinking sine x over cosine x. So we could say this is equal to the limit as x approaches 0. Now, what I'm going to do here, instead of producing a compound fraction, I'm going to do this. Let's say 1 over x times tan x. Okay, I think this will make it easier to see. If I say that, then let's substitute what is tangent of x. Tangent is sine over cosine. Okay, you just have to be careful with when you get compound fractions. I like to factor that 1 over x out and then write tangent as sine over cosine. I mean, you would get the exact same thing if you wrote it as a compound fraction. That's just one more step to worry about. But look at this. Do you see anything that looks familiar? Do you see maybe we have the limit as x approaches 0 of sine x over x. So we can rewrite this as the product of two limits. The limit as x approaches 0 sine x over x times whatever's left over. The limit as x approaches 0 of, sorry about that, of 1, 0 of 1 over cosine x. Okay? What is this limit that we know because we've memorized it? It's 1. Now what's this limit? We can find that limit by direct substitution. So 1 divided by cosine evaluated at 0. Cosine evaluated at 0 is 1, so 1 over 1. There you go. However, had you not known this, had you not memorized this limit, you would be stuck. You would never figure it out. That's why it's really important to have had that limit memorized. Okay? Last example I want to show you, it's another trig example, and then we'll call it a day. This has been a long video. My hand's getting tired, just like you're getting tired of watching this, if you've made it this far. Okay? Last thing I want to look at is the situation. This is a common situation. Limit as x approaches 0 of, say, sine, I'll just make one up, 3x over x. Now, we have memorized the limit, so we've memorized this. The limit as x approaches 0 sine x over x, and we know that equals 1. Oh, I messed that up. Sine x over x, and we know, because we memorized it, equals 1. Now, here's the key thing to realize. It doesn't matter what x is. X is any real number. Well, guess what is also a real number if x is a real number? 3x is also a real number. Okay? So if I can get this function to be in this form, that is, the argument of sine is the same thing as the denominator, then the limit as x approaches 0 will also be 1. So what I can do here is, if I can get a 3 here, so 3x goes there, because 3x is my argument here, because I can't like multiply through by 1/3 to cancel that 3 out, so I get a plain x there. That's not how trig functions work. Okay, but what I can do is, I think I can get a 3 here. Now, how could I get a 3 here? We had that rule back, or it's actually a property of limits, and the property of limits said essentially this. It says if you have the limit as x approaches c of k times f of x, then that's equal to k times the limit as x approaches c of f of x. That means you can factor out a constant. What that also means, so if you're going from this step to this step, it means you can factor out a constant. What that also means is you can bring a constant in. Now here's the key. I want a 3 there on the denominator. Watch what you can do. And this is going to be something that we do a lot here, and then a lot once we get to chapter 5 on integration. Watch this. What if I multiplied by 3 over 3? That is 1, right? I multiplied the limit by 1. Didn't change anything. So I have sine of 3x over x. So I multiply by 1, but what does this property tell me? It tells me I can bring in a constant on that other side of the limit. So watch what I can do. I can leave the numerator 3 out here, but take in the denominator 3. That is, I can take in a 1/3, because 1/3 is indeed a constant. I could say this is equal to 3 times 1/3 times the limit as x approaches 0, sine 3x over x. So I have 3 times 1/3, that's still 1, but let's say I leave the 3 and bring in the 1/3. Then this would be equal to 3 times the limit as x approaches 0, sine 3x over 3x. But now this is just a sine of a number divided by a number. It doesn't matter that it's 3x and 3x or 10x and 10x. As long as it's the same number, the limit is equal to 1. So this, equals 3 times 1 equals 3. Done. This you're going to see a whole lot, so get used to that. Okay? And it uses this really important property right here. That's why it's super important to remember all those properties of limits. We're going to use those for the rest of the course. Okay? All right. Anything else I want to cover before we call it a day? Let's say you had a number there, just a heads up. Let's say you have like a 3 there and a 2 there. Okay? So you have like a mismatch. Well, factor that 2 out and then do the rest of the steps. Factor, or not 2, it'll be a 1/2. So factor a 1/2 out, then multiply by 3 over 3. So you'll bring a 3 in, but you'll be left over here with the 3/2 out front instead of just a 3. So just look out for stuff like that. If you have another number there, it's not hard, just another step. Okay, factor it out, use this rule right here. Looking over the homework, that's about it. You'll probably have some questions. If you have questions, just shoot me an email. Actually, don't shoot me an email. Post on Ask Your Instructor, Ask Your Professor discussion board, and I'll answer you guys there. Again, this is section 2.3. What we've done today is we have looked at evaluating limits analytically. There was 3, well, you always want to try to use direct substitution. If direct substitution fails, there's 3 main techniques. 2 that we use all the time, 1 we use on occasion. The one we use most is the factor and divide technique. Factor your function, divide out whatever you can. Second is rationalizing the numerator. Those are the 2 main techniques we used. The third was the squeeze theorem. We don't use it very often, but what we did here with the squeeze theorem is we used the squeeze theorem to establish some really important trig limits, like this one here, and also this one here. Okay, so we used the squeeze theorem to establish this limit, which then allowed us to establish this limit, which then opens the door for a lot more trig limits. Okay, so Hope it's been helpful. If you guys need any help, don't ever hesitate to ask. Have a good weekend.